Good evening, guys. Please, can I be heard? Hello, good evening, guys. Can I be heard? Okay. Yeah, so once again, we want to welcome you to another class, the fifth class of the series. More people will be joining us. You're welcome once again. Yes, so today's class, we are going to be going further down into the more details, right? But before we get into all of that, we are going to be taking a little bit of background about the academy and the speaker we have, just like we've been doing from class 1. Okay, so my name is Dr. Divine Ewim, and I'm the deputy director of this academy. Our director, Dr. Obianuju, is also here with us. Welcome, Ma. And once again, the Nexus Research Academy is an academy that is purely focused on teaching people and developing minds into producing great research that will be valuable in their various fields. So to be taking us today, we have one of our seasoned speakers, Dr. Kekeocha Martins. I'll be reading his profile briefly while we go straight into the class. So Dr. Kekeocha Martins is a medical doctor, a research and business analyst who is dedicated to discovering insights for clinical research and business. He earned his medical degree from Koyu Chukwuemeka Odumegwu Ojukwu University Teaching Hospital in 2024, graduating with distinctions, and currently practices as a physician while actively engaging in research analysis. Dr. Kekeocha serves as a co-founder of Hidden Leaf Data Analytics and has co-authored 2 peer-reviewed publications in high-impact journals, with additional work in progress and under peer review. Right? So Dr. Kekeocha Martins will be taking us on data analysis part 1. In this class, we are going to be talking about variables. We are going to be talking about descriptive statistics. We're going to be talking about p-value, choosing tests, when to use what test and what other tests, right? So we're going to be starting the part 1 of data analysis today, and I want to beg everyone, pay close attention. You don't know what you will learn today. It would help you. It might help you in the future and sometime later. So do pay close attention and make sure you are jotting and you are learning. Don't waste your time. Make sure you are learning. All right, that being said, we are going to be having Dr. Kekeocha Martins to take the floor. Sir, you are very welcome.
Thank you very much, Dr. Divine, for the introduction. I'm very grateful to be here. Please, I hope everyone can hear me very well. Okay, thank you very much. Yeah, I'll be starting with basic statistics. I just want you to know that most of these things, you've heard them countless times while you are preparing for your exam and whatnot. So it's just a way of refreshing your memory and making you identify key facts that you're meant to know, so that you're no longer scared of, oh, I can't carry out the research because I can't do my statistics on my own. I can't do SPS of my own. So this is just like a beginner class to take you from the nitty-gritty of everything, so that I can be able to identify, oh, these are the tests I'm meant to carry out for this particular research at this point in time, and these are the reasons why I'm choosing such tests. So we'll be going through statistics using this outline: the definition, types of statistics, types of variables, and differential statistics. Next slide. So statistics is just like gathering data. You gather something, you organize, you analyze it, then you bring out a summary and interpret it. When you gather your data and you organize and analyze them, you present the data now as an information. That means the data has gone through different processes that now gives you something that is useful, something that you can use to make a final decision in whatever you're trying to do. So data on its own is a raw fact, is unorganized, is meaningless. You can't make any meaning from it. So it has to go through different processes in order to become an information that can be used whether in healthcare, whether in your business, in anything at all you want to do in life. Okay. So next slide, please. So we are now going over to variables. So when you gather your data, most likely they will be arranged in form of variables in different forms, whether as numbers, as text, or so other types of variables you have
Please, can we mute our mics?
the
Dr. Martins.
yeah, I can hear you.
Yeah, please, could you go back on that slide that you were presenting? Someone's mic was on and we could not hear.
Projecting the slide. Okay, thank you, Dr. Divine. So I'm still on types of variables. We have the independent, just from lay key terms, the dependent depends on something, it relies on something for a meaning. So independent variables, they cause a change in the dependent variables. They are the ones that you don't need to alter them. They are just there. You can't alter them to produce a result. Instead, they alter the result. So we have something like age. Age is something everyone comes with. You can't change someone's gender, level of education, occupation. Instead, these factors can have an effect on other variables. So we now have the dependent variables, which are variables that rely on some other factors for their effects. So a change in an independent variable causes a change in a dependent variable. For example, if we take body mass, for example, using body mass index, body mass index is taken from weight and height. So the body mass index is a dependent variable that depends on your weight and your height for the information. So any altering on the weight or the height is going to change your body mass index. So that is just the relationship between the independent variable and the dependent variable. Also, you can also use an example for example, practice of hand hygiene. Your gender, your age can affect your practice of hand hygiene. Your level of education can affect your practice of hand hygiene. So maybe you can go on and research and see that, okay, most health care workers know more about hand hygiene than any other cadre of workers in the community. So next slide. Also, variables can also be categorized into numerical or categorical, where you have numbers for numerical. Then categorical data just means, or you can use these words interchangeably, whether data or variable. So categorical data just has to do with categories. You have words there, while in numerical data you have numbers instead. Now, under categorical data, they're also called qualitative data. They give a quality to what you are trying to assess. So under categorical data, we have dichotomous data. When there are only two categories in that variable, is either yes or no, you're a male or you're a female, or maybe in an examination, you passed or you failed. There is no in between, just two categories. Now, If your categorical data now has more than two categories, like 3, 4, you now call them nominal variable or nominal data. Example, ethnic group. Example, let's say grading of hypertension. There is normal blood pressure, there is pre-hypertension, and there is the actual hypertension. So there you have three categories. So they are now classified under nominal data or nominal variables. Then we have numerical variables, which are numbers. So the numerical variables are either discrete data or continuous. And just as the name says, discrete means it's on point. There are no two ways about it. You are either here or you are there. So example, you have your age. You can't, yes, some people might tell you, oh, I'm 13 years and but for example, it's written here, age at last birthday. Your age at your last birthday is a definite number. Is either 23 or it's 24. It can never be 24.5. Another example is number of people in the family. Your family members can either be 4, it can be 5. There is no in between. So we also go over to continuous data. They're also called integers because here you can have in decimal points like in kilogram. When you measure the weight of someone, you can get 32.4 kg, 35.4 kg. So there is a value between, for example, if you are using 35.4 kg, 35.4 kg is between 35 and 36. So there's something between it. It's not discrete, it's not focused. Please, next slide. I hope you are not lost at this point. But if there's any question, you can note it down at the chat box or you can write it out where you are. Now we'll now go over to the levels of measurement. Now, these variables that we talked about, the categorical, the numerical, there is a level of measurement, and looking at this chart, from nominal to ordinal interval ratio, they are in an ascending order, meaning that ratio has a greater significance over interval. Interval has a greater significance over ordinal. Now, it will be important to note here that the nominal and ordinal is just mainly for categorical variables, while the interval and ratio scale or level of measurement is for numerical variables. Now, under the nominal level of measurement, here you just have a data label, you just have the categories, there are no orders. You can place them in any order. There is no ranking between them. For example, under gender, you have male and female. None is greater than the other. Yes and no, none is greater than the other. So you just state them for what they are. Then going over to ordinal, this now where there is a rank between each category. Any category you mention has something more significant than the other. For example, we are talking about severity and pain severity, like when you are taking a history from a patient that has moderate pain obviously has more pain than a patient that complains of mild pain. Then, when you talk about severe pain, the rank is obviously better than the moderate pain. So now you are stating these categories, but there is a ranking between each of them, and you must place them in that order for them to have a meaning. Then going over to interval and ratio. For the interval data, they are ordered, yes. You go from 0 to 100. For interval, you can also go as low as minus. So for interval data, there is no absolute value. You can go below 0, you can go above 0. But there's an order. You can write 21 before 11. It must be 0, 11, 21. So there must be an order. But for interval data or for interval variables, there can be -1. Example, temperature. You can have a temperature of 0 degrees. You can also have a temperature of -2, -3. So that is the difference. But going over to ratio, there is an absolute 0. You can't go below 0. For example, weight, there is 0, there is 1, there is 2. You can't say you are weighing -1 kg. That is not possible. You are either weightless, that is 0 kg, and that's where it stops. Same thing with height. Okay, we'll go over to the next slide. Now, we are going over to the types of statistics. So the major difference between descriptive and inferential statistics is that in descriptive statistics, you are talking about something that has already happened. You are looking at a set of data and you're giving a summary and analysis of something that has already happened in a population. You're just bringing out insights of what has already happened. For example, you have age. For example, you have mean, you have frequency. Frequency, number of times of occurrence of a particular outcome, something that has already happened. But inferential statistics, you are trying to make an inference. You are trying to say that, oh, if such thing has happened in this population, we can infer or we can suggest that it will also happen in this other population. So you are making a guess. But now you have to now prove using statistics to prove that, oh, this is statistically proven that this can be possible in such population. So for example, in descriptive, please go over to the next slide. Under descriptive statistics, you have your measures of frequency, measures of central tendency, you have measures of variability. This literally tells you what has already happened in data. Okay, go over to the next slide, sorry. So under measures of frequency, you can represent them using frequency tables where you have the variable, the frequency, which is number of times of occurrence. You can express it in percentage. You can also show your measures of frequency in form of bar charts, a column chart, a line chart, or even a pie chart. Now, under measures of frequency, you can divide them into comparison, composition, and relationship. Yeah, some people might come up with the question of how do I choose the best visualization for a data? How do I represent this data in the best format? So the first question you have to ask yourself is, are you trying to compare two variables, or are you trying to variables are each other, or are you trying to show a relationship between probably a dependent and an independent variable? For example, when you want to compare when you want to compare a data, for example, you carry out a research and under your age, you've classified your age into different age groups, let's say 20 to 24 years, 25 to 30 years, 30 years and above. You can use a column chart or a bar chart to show that, okay, most of my population that fall within 20 to 25 years are for this bar chart, for this column. Then 25 to 30 are for this column. So it shows a comparison between these different age groups just for visuality. So now we are comparing two things. Then when we come over to composition, are you trying to show that, okay, we want to know out of this my population, how many people are females, how many people are males? So it's important for you to know that you can use a pie chart to show comparison. But whenever you're comparing variables and it's more than 5, it's not advisable to use a pie chart. So when the number of things you are comparing are more than 5, it's not good to use a pie chart because one, the calculations might not be as accurate as it's meant to be, and to not give the clear picture because the person has to start zooming in to know which one is for which. So whenever what you're comparing is more than 5, you can choose a bar chart, which can be better, or you can choose a tree map. Then going over to relationship, if you're trying to check for a relationship between a dependent and an independent variable, you can use a scatter plot or a bubble chart. For example, if you are comparing weight and height, no, if you are comparing BMI and height, so you plot your BMI on your y-axis while your weight is on the x-axis. Then you can also, for the bubble chart is now when you are comparing 3 different variables, but you want to express it on a visual chart, you can use a bubble chart. The bubble chart is going to give it a 3-dimensional outlook, in the sense that a bubble chart is like a scatter plot that now has, let's say, like an area. For example, if you are comparing with BMI with age, Now, between these three factors, you know that your weight is going to be increasing with your age. And as your weight is increasing, your BMI is also increasing. So looking at this bubble chart, the bigger circles shows that both three factors are larger than the ones with the smaller circles. Probably the weight and the height and the BMI, the weight, the age, and the BMI are on the extreme side. That is why their own circles are bigger. So it's when you are trying to compare, look for a relationship between three different variables, you can use a bubble chart. That will help you to show it properly. Okay, next slide, please. So we go over to measure of central tendency. So this measure of central tendency is more like telling us you are trying to bring out a single value that tells us the center of your data. Your central tendency meaning a single value, a single point. For example, mean is a measure of a central tendency. A mean is a single value that tells you the average of a variable, mostly in numerical variable. For example, you have different ages in a population and you look for the mean age. That is one value. Then you can also, there are other values that are both on the right and the left side of that value, but the mean tells you just one value that can represent that whole population. Also, we have median. Median is calculated by when you arrange your numbers either in ascending or descending order, you pick the number at the middle. For odd numbers, you have one value. For even numbers, you take the two middle numbers and divide by two to give you one single number around which other datas are going to be drawn out, but that median is going to give you just one single number. You also have the mode. Mode is one number that occurs the most frequent throughout the data, the most occurring number in the data. So there are different times where you use a mean, there are different times where you use median, there are times where you use mode. For example, if your data has much outliers, it's not advisable you use mean because those outliers are going to make your data to be skewed. For example, you take a data among university students, most students that you're going to get, they are going to be probably within the ages of 19 to 25, 26. But you can still find outliers that are almost 30, 32, 34, thereabout. So if the outliers are much, you can't use the mean because those outliers are going to affect the result of your measure of central tendency. Thereon you can use mode, you can use median. So you can use median, so you can arrange all the ages according to the order, then you pick a single number. So you also have measures of spread. So under measures of spread, you have range, standard deviation, and variance. So range is just the difference between the highest number in your data and the lowest number. Then the standard deviation tells you how other data deviate from the mean of your data. So it's telling you how spread out your data is. So all this just tells you about what has already happened in the past. So you have your mean, measures of frequency, you have your range and your standard deviation. Thank you. Please can you go to the next slide? So you have a normal distribution. Normal distribution is also measures of spread. So this is like a graphical representation of how your data appears. So you plot, let's say these are ages of children in a pediatrics clinic and their frequency. So this is a normal distribution sample. It tells you that, oh, this data is normally distributed. So from a normal distribution, you find out that the mean is at the center, at the peak of the curve. So usually it has a bell shape. This is the next slide. Then the characteristics of a normal distribution. This is very important because as time goes on, you have to use this knowledge to understand other things that we're going to talk about. So in a normally distributed data, you find the mean at the middle of the distribution curve and you divide your data into half. So it says that 68.2% of all values will fall between +1 and -1 standard deviation. Please can you go to the next slide? I think the picture will explain it better. Okay, next slide. Okay. No, go to the previous slide, sorry. There was a diagram that was meant to be here, sorry. So 68.2% is meant to fall between plus and minus of the standard deviation. So we have 95.45% falling between plus 2 and minus 2 of the standard deviation of the mean. Okay, go to the previous slide. Mm, Okay, taking this picture for an example, the mean is at the middle of 7. I don't know if you can see what I'm pointing at. The mean is at the middle of 7. So let's say plus and minus 1 of the standard deviation should be 6 and 8. The sentence in the next slide says that 68% is going to fall between plus 1 and minus 1. That means 68% of your values are going to fall between 6 and 8. 95% are going to fall between plus and minus 2 of the standard of your mean. So that means 95% is going to fall between 5 and 9, which is plus 2 and minus 2 of 7. Same thing with 99%. 99% is going to fall between plus 3 and minus 3 of your mean. So that is going to fall between 3 and 10. That is what the next slide is all about for a normally distributed data. Okay, go to the next slide. But you have to understand that in reality, when you carry out all these researches, your distribution might not always be normally distributed. So sometimes you might have outliers. For example, if you are carrying out a research of the prevalence of hypertension, you find out that most of your age group that are hypertensive are going to be on the left side of your dependent variable axis, your independent variable axis, which is the age, because they will be at a higher age. So you find out that your data is most likely going to be negatively skewed, the picture on your left. But if you are carrying out your data, let's say about breastfeeding, and you're going to a pediatrics clinic, you find out that most of your data might be between children that are infants. Most of the data are going to find there are mothers with their children which are less than 1 year. So most of your data is going to be on the left side of the graph, which is the positively skewed distribution. The next slide. So we have inferential statistics, which I've talked about. So you are making a generalized comment on a population based on what you found out in a sample population. So under types of inferential statistics, we have the estimation theory, we have hypothesis testing. So next slide. So we have point estimation. So point estimation just means we are using a single value to make an inference on a general population. And what you have to understand is that for you to make an inference, your sample population should be ideal or should represent your population, the actual population you want to study. For example, you want to make a research about hypertension in the southeast. You can pick, let's say for example, our hospital, Chukwemeka Odumegwu University Teaching Hospital, Anambra State, which is in southeast, and say, okay, based on this, I can make an inference on southeast. But it will not be ideal for me to make a research about prevalence of hypertension in Amago Teaching Hospital and make that generalization on the whole of Nigeria. Is going to be out of place because that sample is not representative of a population. So for point estimation, you have a single numerical value. An example is you measure the weight of 50 newborns and you get a mean weight of 3.2 kg in a hospital. So you can now infer that, okay, the average weight of newborns in this hospital is 3.2 kg using a single numerical value. That is just what point estimation is about. Another example is you make a research about prevalence of diabetes, and out of 40 patients, you have 40 people who are diabetic, giving you a percentage of 20%. So 20% is that single numerical value. So you can use this to infer or make a guess on what the general population looks like. Then we have interval estimation, or using the confidence interval. So in interval estimation, you use a range of value to make your inference. For example, you measure the systolic blood pressure of about 100 adults, and you had a mean of 20 millimeters of mercury for the systolic blood pressure. Then using this value, for every for every confidence interval, there is a corresponding z number to calculate the ideal confidence interval for that confidence interval. So for example, you have 95% confidence interval. Using z as 1.96, then you calculated and you got 120 millimeters of mercury, which is your mean, plus or minus 1.96 of millimeters of mercury. So using what I said about the normal distribution curve, for a 95% confidence interval, you are not making an inference that 95% of everybody in this hospital are going to fall within 118.04 to 121.96 millimeters of mercury for their systolic blood pressure. That is what interval estimation or using confidence interval for your hypothesis testing means. Then next slide, sorry. Then go over to hypothesis testing. We are done with the point estimation or the estimation theory. Now, under hypothesis testing, a hypothesis is an intelligent guess, an unproved statement that you formulate before you start your research, because your the aim of your research is to find out if this your guess is true or not, and if it's true, is it statistically backed, or is there a statistical backing that can show that for sure this actually happens, or did you just happen to find it by chance? So whenever you make out your hypothesis, is either have a one-tailed hypothesis or a two-tailed hypothesis. For example, let's say we administer drugs A and B to a patient. For one-tailed hypothesis, we just want to know if drug A is better than drug B. So you carry out your research. So you answer the question, yes or no, drug A is better than drug B. If it's no, you say it's no. But for two-tailed hypothesis, we want to know if there is a difference between these two drugs and what is the direction of that difference. So first, there is a difference between drug A and B, yes or no? You probably say yes. Now, is drug A better than drug B, or is drug A worse than drug B, which is now the direction? So first, you establish that there is a difference. Then you tell us the direction of the difference, whether this is worse than this or this is better than this. Then you have your null hypothesis and your alternate hypothesis. So under null hypothesis, we are trying to say that there is no difference between drug A and drug B. That is what your null hypothesis will be. Then your alternate hypothesis will be there is a difference between the outcome of people that take drug A and drug B. So that is for alternate hypothesis. Okay. Then we have parametric tests and non-parametric tests. These are the types of parametric tests. So in order not to confuse us, because sometimes this is where the confusion comes in, parametric tests are only carried out when your data has normal distribution. Then non-parametric test is carried out when your data does not assume a normal distribution, or when you have an ordinal data, like we said in the categorical variables. So go over to next slide. Next slide, please. So I will just go through this test as what they are. Then later on, we'll classify them into whether they are parametric or non-parametric. So for example, we have the t-test or the student t-test. So the t-test or student t-test is used to compare the mean between a sample and between a sample's mean and the mean of a population. So under t-test, you have the one sample t-test. So in one sample t-test, we are comparing the sample mean, just one sample, with a population mean. So for example, you have the weight from 30 patients. So you go to a clinic and you measure the weight from 30 patients. You probably want to do a research on them. So you measure their weight. So You want to compare the mean of their weight against the population mean. So using this formula, you can calculate the t-value. Then there are other things you are going to do after that. So when you want to compare a sample mean and a population mean, you use one sample t-test. Next slide, please. Now we have paired t-test. So from the name implies paired t-test. So you have two measurements from one person. So the people you are measuring the people you are trying to get a data from, you are getting two data from the same person. So you have a pair for one person. For example, weight measurements from same subjects. Weight measurement from the same subject at 6 months interval. So you come to clinic, you measure the weight of your patients. Then after 6 months, probably you give them drugs or you place them on a nutrition program. You want to know their weight after 6 months from the same subject. So you use a paired t-test. Then you have two sample t-tests or unpaired t-tests. Now you get different variables from different subjects. So the example we use there, we use weight measurement from infants who are breastfed with different formulas. So you group, let's say about 30 infants into a group of threes. Then you tell your mother to place them on these three different infant formulas. Then after like 6 months, you want to know their weight and know if there's a difference between the weight. So you have three different groups. They are no longer in pairs, they are just separate. So you use the unpaired t-test. Next slide, please. Then you have the z-test. The z-test is used to compare a sample mean with a population mean. And another condition for you to use a z-test is that the sample size must be greater than 30 and the population standard deviation must be known. For example, life expectancy of northern Nigerian men. Let's say a research was carried out in northern Nigeria and we found out that life expectancy for northern Nigerian men was 75.32 years. But the life expectancy for Nigerians as a whole is 54.6 plus or minus 11 years. So we want to test if this 7.5 is statistically different from the 54.6 plus or minus 11 years. So there you use a z-test. Then we come to ANOVA. ANOVA involves comparing the mean between three or more groups. For example, when we are at the paired t-test, we are comparing one group that had the same features, one person having two variables. When we went over to the unpaired t-test, we are comparing the mean between two different samples. But in ANOVA, you are comparing three or more groups. So, for example, you want to examine the weight of infants at 1 year, taking formulas of up to 1, 2, and 3, or even 4. If you are to use the unpaired t-test, you can only compare for 1 and 2 first, 2 and 3, probably 1 and 3, before you can get your conclusion. But an ANOVA will help you to compare the three of them along the straight line and give you your significant value. Next slide. Now we have the chi-square test. The chi-square test is used to test for association between categorical variables. For example, level of education, knowledge of antibiotics, knowledge of analgesic misuse. So these are categorical variables, they are not numerical variables. So if you want to test for association between these type of variables, you can use a chi-square test. So we also have a Fisher's exact. Probably in our next class, I'm going to talk more about this Fisher's exact. This next slide. Then we have correlation analysis. The correlation analysis is used to test for strength and association between, mostly use correlation analysis for either a numerical variable or a categorical variable. For example, we have the Pearson's coefficient. Now, in the Pearson's coefficient, it tells you whether there's a relationship between numerical variables and the direction of that relationship. For example, we know that there is a relationship between your blood glucose level and your CSF glucose, because obviously when you eat your food, the glucose first gets into the blood before it diffuses through the blood-brain barrier into the CSF and all what that do. So there will be a relationship between what is obtainable in the blood and what is in CSF. So this relationship was gotten as CSF glucose equals 2 over 3 of plasma glucose. So whatever you get as your plasma glucose, you multiply it by 2, divide it by 2, that is your CSF glucose. So this 2 over 3 is a plus, is not a negative, because as your plasma glucose is increasing, your CSF glucose is also increasing. So the 2 over 3 tells us that the relationship is in a ratio of 2 over 3, and the direction is in the positive side, because as one is increasing, the other one is also increasing. Then we have the Spearman's rank. The Spearman's rank just tells us if there's a relationship, whether there's no relationship, or if it's increasing or decreasing. It does not tell you both. For example, relationship between the dosage of analgesic and pain relief score. And here it is written that the Spearman's rank must not give you a linear relationship like the plasma glucose, which is 2 over 3. As one is increasing, the other one is also increasing. Here, you might have a direct relationship where as one variable is increasing, the other one is increasing. But at a point, there might be no difference. For example, if a patient is in pain and you give an analgesic, let's say paracetamol, let's say 300 milligrams, the patient's pain relief is going to be less compared to someone you administer 600 milligram. That person is going to get at least a better pain relief outcome. But even if you increase the dosage above 600 milligram, you might still not get any difference in pain relief because you've missed a maximum point. So the data is no longer going to be, the relationship is no longer going to be linear. It's going to have like a plateau where you have the maximum point and any other thing is probably diminishing return or no return at all. So next slide, please. So linear regression is also a test for hypothesis, but here you try to predict an outcome in regression analysis. So under linear regression, we use it mostly for numerical variables. So you have variables used around age and age, BMI, and systolic blood pressure. Your age in years, 22 years, 24 years, and the blood pressure. And you want to know if someone's age can predict their systolic blood pressure. So you can use a linear regression analysis. So you can have simple linear regression when you are considering just one predictor variable, just age. But when you're considering more than one predictor variable like age and BMI against systolic blood pressure, you start using multiple linear regression. Then you have logistic regression. So logistic regression is now when your variables are categorical variables. You can no longer use linear regression. You have to use logistic regression. So all your variables are categorical variables, and you're trying to know if one can predict the other. For example, does level of education predict booking at first, second, or third trimester of pregnancy? So your predictor variable is level of education, which can be primary, secondary, tertiary, while booking trimester can be first, second, or third. So you want to know if if the level of education can predict that, oh, most people that have higher level of education book earlier than probably people that have lower level of education. So is there another slide? So this is just like a summary of all this. Then I guess from here I can take the questions if there are any questions so far. Thank you.
Okay, thank you very much, our speaker, Dr. Martins Kekeocha, for that insightful lecture. And before we take the questions, I just want to announce that in our next class would be the practical. Dr. Martins has been saying a lot of things. So in the next class, we would go in details into the practical. All right. So please, if you do have any question, can you just raise up your hand? Let's take the questions. Please, if you do have a question, can you raise up your hand? It can only mean two things. It can either be you understood it perfectly or you are confused. Please, if you do have a confusion, you can ask your question and to be sorted out.
Please, you can also type in the chat box if you don't want to speak. We'll also see the messages there.
Okay, okay, seems there is no question. Okay, so next class, Dr. Martins will be sharing his slide and will be understanding more in terms of, looking at the SPSS software and understanding better all he has said in today's lecture. I know it's data analysis can be a little bit overwhelming for newbies like us, but I would do encourage us, maybe after this class you can do well to go to the YouTube channel and sit back and probably listen again to where you were confused. Take out time and try to go over it again. You can get new points from what he shared this night. Okay, I also want to use this opportunity to say that the director of this academy was here, but she left at some point due to network issues. She's sending her regards. Okay, so that being said, without any other questions, I think we've come to the end of today's meeting. I want to thank Dr. Martins for bringing out his time to share this insightful lecture to us. Thank you, everyone, and do have a blessed night.